Hello, everyone, and welcome to today's Explainer. I am absolutely thrilled to guide you through this session because we're taking a truly hands-on journey today. We're going to take the abstract, sometimes intimidating mathematical theory behind digital signal processing, or DSP, and translate it directly into practical working Python code. If you've ever wondered how the physical world gets processed inside a computer, well, you are exactly in the right place. Grab a coffee, get comfortable, and let's get into it.
Here's our roadmap for today's lab. First, what is digital processing? Second, the Python DSP toolkit. Third, Python coding essentials. Fourth, generating a sine wave. And finally, plotting complex signals.
Section 1. What is digital processing? From physical quantities to data.
Okay, let's dive into this by grounding our understanding of what a signal actually is out there in the real world. To build our foundational toolkit, we really have to distinguish between three distinct types of signals. First up, the analog signal. This is a function that is completely continuous in both amplitude and time. Think of it like a smooth, unbroken wave. Next, we step toward digitization with a discrete signal. Now, this one is still continuous in its amplitude, but it's only defined at specific, discrete intervals of time. It's like taking rapid-fire snapshots of that continuous wave. And finally, we have the digital signal. This is where the magic happens for computers. It's a discrete signal where the amplitude values are quantized into finite specific levels. At this stage, it's fully prepped for a digital computer to read and manipulate.
To brilliantly illustrate this idea of quantization, just think about taking a photo with a digital camera. Kind of like the mirrorless one right here. When you snap that photo, you are creating a digital signal. Specifically, it's a 2D spatial signal. Now, if this happens to be an 8-bit digital image, it means the continuous physical light captured by the camera sensor is quantized into exactly 2 to the power of 8, or 256 distinct grayscale levels. So that infinite physical light from the real world is now locked into finite digital data. Pretty cool, right?
So, what does this all mean, and why does mastering it matter? Well, because DSP is literally the backbone of our modern world. Consider these massive global industries. In speech processing, DSP is the engine used for voice recognition on your smart devices. In telecommunications, it's what runs your mobile phone and keeps satellite comms functioning. In seismology, we use it to detect and locate earthquakes. In the medical field, it processes life-saving ECG and EEG signals, allowing doctors to read heart and brain waves. And it's even the core logic behind radar target tracking. Entire industries are completely 100% reliant on digital signal processing.
Section 2. The Python DSP toolkit, setting up your new workbench.
Now that we know what DSP is and why it's so important, let's look at the modern toolkit. Traditionally, older languages like MATLAB really dominated this field. But today, Python has completely taken over, mainly because of its open-source nature and some incredibly highly optimized libraries. For our workflow today, we're using Spyder, which stands for the Scientific Python Development Environment. This is a powerful, integrated development environment designed specifically for scientific computing. Let's take a quick tour. On the left, that's the editor pane where you actually write, edit, and save your scripts. On the bottom right, you have the interactive IPython console. That's where you can execute code on the fly and see immediate text outputs. And right above that is the plots pane. That's going to be your best friend because it automatically displays all the visual graphs we'll be generating. It's an incredibly intuitive setup once you get the hang of it.
Now, Spyder comes preloaded right out of the box with some heavy hitters like NumPy and SciPy. But since we're doing advanced DSP, you're going to need to add a few specialized tools to your new workbench. To do this, you just navigate down to that IPython console we just talked about, and you use the pip install command. Specifically, we want to type out pip install lkp control neurokit2. You just type that in, hit enter, and Python will reach out to the internet and pull these specialized libraries straight into your local environment. It's that easy.
Section 3. Python Coding Essentials, the building blocks for signal generation.
With our workbench fully prepped and ready, let's transition into the basics of Python syntax. Think of these next few steps as learning how to use the fundamental hand tools you're going to need for our upcoming digital builds. Let's start with getting your code to actually talk back to you. The print function is how Python pushes text, variables, or the results of math operations directly to your screen. For example, enclosing words and quotes inside the parentheses, like print hello world, outputs that exact string of text to the console. It might seem basic, but it is absolutely crucial. It's going to be your primary diagnostic tool when you want to see what's happening inside your program.
Next up, we need a place to store our data. While standard Python lists are okay for basic things, they really aren't great for heavy math. And DSP is all heavy math.
That's why we import NumPy and use NumPy arrays instead. You can see how we define it here. MyArray equals np.array. Arrays are vastly more memory efficient and performant than standard lists, especially for manipulating the large, homogeneous collections of numerical data we see in signal processing. And here's the real game changer. Notice how we can instantly add 10 to every single element in the array with just one simple line of code? You don't have to manually update every number. NumPy does the heavy lifting for you instantly.
Now, what if we want to perform a repetitive task automatically? Like, say we want to go through a massive data set piece by piece. That is exactly where the for loop comes in. By writing for num in numbers, we're explicitly telling Python to iterate through every single item in our dataset one by one and execute the indented code directly below it. In this specific case, it just prints the number. But imagine having thousands of data points. This structure saves us from writing endless lines of redundant code. It literally loops over the data for us.
Let's actually apply that loop to a real numerical analysis task, finding a sum. Let's trace this step by step. Look closely at lines 4, 5, and 6. We start by creating a variable called total_sum, and we set it to 0. Think of it as an empty bucket. Then the loop begins. For value in data, total sum equals total sum plus value. So, step by step, the script takes whatever is currently in the total bucket, pulls the next value from our array, adds them together, and updates the total bucket with this new higher number. It just keeps spinning through that cycle. By the time the loop finishes its final pass, we have our complete final sum.
Beyond just looping through data, your Python scripts will often need to make dynamic decisions based on variable inputs. This is handled by conditional logic blocks using if, elif, which is short for elsif, and else. Let's walk through this grading example. If the score input is greater than or equal to 80, the code immediately executes the grade A+ print block and skips the rest. But if it's not 80 or higher, it moves down to the elif to check if it's at least over 40. And if all else fails, the final else block triggers as a catch-all. It's a very clean, top-down decision tree that allows your code to react intelligently to different data.
Now here is a critical best practice you have to remember. In Python, white space is functional, not just aesthetic. Correct, consistent spacing is literally what groups your logic blocks together. Look at the comparison here. Misaligned spacing, like a misplaced tab on the right side, doesn't just look a little messy, it fundamentally breaks the execution flow and will instantly trigger an indentation error when you try to run it. Python uses that empty space to understand what code belongs inside a loop or an if statement, so always mind your spacing.
Section 4. Generating a sine wave. The final build.
Okay, now for the really fun part. We are finally putting all of our tools together to generate an actual continuous time signal. But before we write the code, let's ground ourselves in this theoretical math equation. This is the core mathematical expression for a continuous sinusoidal signal. Let's break it down. X of t represents our signal output over time. The capital A right in front is the amplitude. That represents the peak voltage or how tall the wave gets. The lowercase f is the frequency, which tells us how many complete wave cycles occur per second. And finally, that Greek letter phi at the end indicates the phase shift, which basically dictates exactly where the wave begins its journey on the graph.
Now, translating that pure math formula into a functioning Python script requires 4 structured steps. First, we have to define a timescale array, and we use NumPy's linspace function to do this. This basically creates our horizontal x-axis time points. Second, we set our variables for the signal parameters we just discussed: amplitude, frequency, and phase. Third, we write out the actual sine wave expression using the np.sine function, multiplying our variables together just like the formula. And fourth, we push all of that generated data to our Matplotlib library to actually draw the plot on our screen.
And here is the incredibly satisfying payoff. Those basic steps we just coded generate this exact, perfect visual representation of physics. Let's look at the results. Because we defined our amplitude variable as 5, you can see the peaks hit exactly 5 and -5 on the vertical y-axis. We set our frequency to 5 Hz, meaning if you look across that 1 second x-axis at the bottom, you can trace and count exactly 5 complete wave cycles. It is a one-to-one perfect translation from abstract theory directly into coding practice.
Section 5. Plotting complex signals, phases, and subplots.
Now, real-world engineering rarely deals with just a single simple wave in isolation. What if we need to analyze multiple phase variations simultaneously?
Well, we can use a for loop combined with an array of distinct phase shifts, like 0, 90, 180, and 270 degrees. But if we just plot them all on top of each other on one single axis, it creates a very messy, unreadable output. Instead, we use plot.subplot. This amazing function lets us neatly arrange these different waves into separate, distinct grid spaces within a single overall figure. And here's a huge pro tip for you. Always apply plot.tight_layout at the very end of your script. It automatically calculates the perfect spacing between these subplots, so your axis labels and titles never overlap and create visual clutter.
Sometimes, though, we actually do want to generate overlapping complex signals on the same graph, like when we're modeling a three-phase sinusoidal signal. This specific concept is absolutely crucial in modern electrical power distribution and telecommunication engineering. It's how the power grid works. The math dictates that these three signals share the exact same amplitude and the exact same frequency, but they are mathematically offset by exactly 120 degrees from one another. So phase 1 starts right at 0 degrees. Phase 2 starts offset at 120 degrees, and Phase 3 starts offset at 240 degrees.
Now, when you do plot multiple lines on a single graph like that, we have to apply finishing touches to make the data actually understandable to humans. We use plt.xlabel and yLabel to clearly define our axes. We use plt.title for a descriptive header, and crucially, we use plt.legend. By passing an array of strings, like phase 1, phase 2, phase 3, directly into the legend function, Matplotlib will automatically color code a nice little key box. This ensures anyone viewing your chart knows exactly which colored wave corresponds to which phase. It's the difference between a good graph and a great professional one.
And just like that, that wraps up our step-by-step DSP Lab explainer. But before we go, I want to leave you with a direct challenge to test out your brand new toolkit. Here's your mission. Can you write the Python code to generate a sinusoidal signal with an amplitude of 2 volts, a frequency of 10 Hz, a phase of 0, and, here's the really tricky part to think about, a length of exactly 3 continuous periods? Open up Spyder right now, get your NumPy and Matplotlib imports set up at the top, and start coding. Thank you so much for learning with me today. You guys did great, and I'll see you in the next explainer.